Hello, this video is going to mostly be on semiconductors, but before I get on to semiconductors, it's worth saying a little bit about conductors and insulators, because semiconductors sit in between the two. So conductors, as we know, we're really thinking about a lot of the metals here, which has got a lot of mobile electrons. Yeah, they're not electrons that are tightly bound up to particular atoms inside the structure of the metal, and these can move around relatively freely. Then for insulators, you've got the opposite. There are very few mobile electrons. So we're looking at things like glass, ceramics, rubber, plastic, things like that, even paper. And here you just don't get current flowing because you need charge to be able to move if you want an electric current to flow. Now, of course, you can, if you've got a large enough potential difference put across a particular material, then you will get a current flowing. You know, this is even the case with insulators, that if you put a large enough voltage across an insulator, you know, what's known as the breakdown voltage, then you'll start ripping electrons away from atoms and they'll start flowing around. So it's like you're pulling these electrons out from atoms, you're pulling them out from bonds between atoms, and then having them move because the EMF, our electromotive force, is so strong that it can overcome that. But by and large, we're talking about insulators as being things which don't allow current to flow. So what's going on then with semiconductors? Well, as the name suggests, they're sitting in between conductors and insulators when it comes to allowing electrical current to flow. But it's more than just that. There's another feature of semiconductors that is really, really important, and that is that they have what's known as large negative temperature coefficients. And that means that their resistivity will drop, and therefore their resistance will drop as the temperature increases. So this is different to most other materials. So I'll come back to this later on when we're seeing the applications of semiconductors, but this is something which is particularly important. Now, when we're looking at the resistivity, and remember that resistance of a particular shape of material or particular construction, a resistance of a component is proportional to the resistivity. So for resistivity, we're looking, so for copper, that's around, and silver and things like that, we're looking at around about, I don't know, 10 to the minus 8, that sort of order for our resistivity. This is all in ohm meters, remember. So this is just our generalized measure of resistance, really, without the material being turned into a component. So we can just compare material rather than component when it comes to how much resistance to electrical current they're going to provide. So we've got that sort of level for a conductor. For an insulator, so something like glass or diamond or that sort of thing, well, air is another one, air, wood, paper, that sort of stuff. We're then looking at 10 to the 12, 10 to the 15, that sort of thing. So massive, we're looking at 10 to the 20, 20 orders of magnitude difference here between a conductor and an insulator. The semiconductors, so let's take the most famous silicon, silicon chip fame. You're looking at, say, 2,000, 2,500, something like that. So we're sitting, pretty close to being halfway between the two here. But this resistivity will decrease as the temperature goes up. So this might be the resistivity at, say, 20 degrees C, but then this is going to drop and it's going to start acting more like a conductor as things get hotter. And this is particularly important for, well, pretty much everything that we use in electronics nowadays. Sensing circuits and things like that. This is how our light dependent and such like resistors and thermistors and things like that are working. Right, so how are we actually setting up, how are we using semiconductors then in circuits nowadays? So we can change the conduction properties of semiconductors even more by doing this thing called doping, where you're putting impurities into the structure of the crystal structure of the semiconductor. So say we've got some silicon, you could then dope this silicon in order to change the number of charge carriers that are going to be available and change its response to variations in temperature. And there's two different types of charge carriers that we need to think about when we've got a semiconductor. So we're not just thinking as we were with conductors. So in a conductor, we were just thinking about these free electrons. So we've got electrons which are just sort of, ready to go. Pretty much, they're not closely tied to any atoms. They're not in atomic bonds and all of this. This is in a conductor. You apply a PD and they're all just off. They all just start moving. So that is great. Semiconductors, things a little bit different. So we've got the conduction band and we've got the valence band, and the electrons can live. They can be existing in either of these bands. And the thing with semiconductors is these bands are quite close together, which means electrons can start hopping in between the two bands, which is what's happening when we got these temperature changes. Things heat up, we're getting electrons jumping out of the valence band into the conduction band, makes it more conductive. When it cools down, they're going back again from the conduction band to the valence band. In an insulator, that just doesn't happen unless you've got huge potential differences. The electrons are all tied up in the valence band. So this is what's going on inside the semiconductor. So inside the conduction band, we're thinking about these free electrons that are moving around. Inside the valence band, we're thinking of these things called holes, which are sort of spaces where electrons can exist. If you think of what we were saying in the structure of matter section, remember electrons need to be in unique quantum states because of the Pauli exclusion principle. So inside all of these bonds between, in the crystal structure of the semiconductor, there are certain places that the electrons can be. And if you've got a gap, then that is what's called a hole. Now, this comes down to different ways of how you can describe charge, because we could say, oh yeah, well it's the electrons that are actually moving around. If this electron moved from that spot to that spot, then we've actually had a movement of negative charge. But that's not necessarily the easiest way to describe everything. You could describe it that if we've gone from some situation where that's the hole to some situation where that's the hole in this grid of 9. So it's moved from the one in the center. If you can't see all the dots I've drawn, it's moved from the one in the center to the one off to the right. Well, it might be easier to just say, well, actually the hole has moved. So it's like saying that a positive charge has moved from the center to the right. It's like that analogy of if you've got one empty seat in a theater and all the people move around, is it easier to describe the movement of all of the people in the theatre if they all get up and move to a different seat? Or is it just easier to say, well, all the people are much the same, all we care about is where the new empty seat is? Let's track the whole, let's track the empty seat rather than the movement of all the people. So that's how we can describe things here with these movement of holes. So we've got two different ways then of describing the movement of charge inside this semiconductor. We got the movement of electrons in the conduction band, and we got the movement of holes in the valence band. So when coming back now to doping, there's two ways you can dope a semiconductor. You can dope it with holes. So say that's often done, you might dope it with boron. That is adding holes. That gives us more holes, which means we're getting more positive charge, really, because these holes are absence of negative charge, they're positive. So you get what's called a P type, P for positive, semiconductor, because we've doped it with holes. Or you might dope it with electrons. So if you put in some phosphorus, then you get more electrons, and you get, you guessed it, N-type for negative, N for negative, and that gives us an N-type doped semiconductor. So we've now got these P-type and N-type semiconductors when they've been doped up. And that means we've got more charge carriers, but it also means we get some very interesting behaviors when you put these two types of semiconductor next to each other. And this is pretty much the foundation of all modern electronics, is based on the junctions between these different types of doped semiconductors. So before I get onto those, let's just do a quick recap of what I've said about semiconductors so far, because there's quite a lot going on. So in terms of their conducting properties, they sit halfway between conductors and insulators, but they have that unusual property of, as they heat up, their resistance will drop, which is the opposite of what you get in conductors. And that's because of this movement of electrons between valence band and conduction band. So that makes semiconductors particularly good for sensing things, because they're subtle to changes in environment, which means we can pick up changes in environment based on the change in resistance of a semiconductor component. Because if the resistance changes, you're going to get a change in current, you're going to get a change in potential difference and such like. So they're great for sensing things. Right, now let's get back onto the these P-type and N-type doped semiconductors then. So let's go for diodes. These come up quite a lot. We see these things, we know our IV characteristics for a diode, as in they allow current to pass in one direction. So if we've got our I and our V, normally we're getting no current flowing until we reach some kind of threshold voltage, and then the resistance drops off rapidly after that, and we don't get any current flowing in the opposite direction until we reach some kind of breakdown voltage, where essentially we're destroying the diode, we're damaging the semiconductor. So we've got some threshold voltage that then allows a current to flow at low resistance. So what's going on in a diode? This is where we've got a junction between P-type and N-type doped semiconductors. So we have a P-N junction. Now, for the symbol for a diode, the arrow points from the P to the N, because we're talking about conventional current. Now, we know that the electrons are moving the other way, which kind of makes sense, because if we've got all the electrons sitting in here, comparatively speaking, we know that the electrons are going to want to go from the negative to the positive. But that fits in with our, conventional current going from positive to negative, electrons going the other way. So when you put the P and the N together, the P-type and the N-type, you get in the middle here at the join, you're going to get something called a depletion zone, because you're going to get some crossing of the boundary. You're going to get some electrons will move from the right to the left. They'll fill in the holes. You've got all these holes waiting for electrons on the left-hand side. We've got all these electrons sitting there on the right-hand side. So some of them just pop across the gap and they start filling in the holes. So you get this sort of neutral depletion zone, which is sitting in the middle. This will continue to happen if you give them a little bit of a push. Essentially, if you put a potential difference in the right direction across this junction, you're going to give enough of a push to some of these other electrons that they'll start going across the boundary here, and it will start flowing. You're going to start getting this movement of electrons, and they'll just sort of start cascading, because they have to keep moving. They're not just going to go across. So you think of Kirchhoff's first law, we have to have the same current going all the way through this. So you're getting this cascade of electrons as they sort of ripple through these holes. Now, it doesn't have to be the same electron, but you're getting this movement of electrons, which you, of course, as I was saying earlier on, you could think about as being movement of holes. It's the same thing, depending on how you want to go about describing it. So you can think about holes moving to the right or electrons moving to the left. The effect is the same. but you're getting this movement. It's allowing, if you give them enough of a push, if we've met our threshold voltage, then you're going to get this movement of electrons from the negative to the positive. But of course, if you put the potential difference the other way round, that just isn't going to happen, because you just don't have the we've got a build up of negative charge here in the n-type semiconductor, which is stopping electrons really coming across this gap. You might have some stuff here in the wires which is, oh yeah, this is great, let's start making our way across here, but it's not going to start rippling through here in the way that it does in the other direction, because you've got this blockage here. You've got this net sort of negative charge which is pushing these electrons away. It's stopping stuff from flowing. And this is a simplified view of what's going on, but in terms of an intuitive view of a diode, you can see how that's going to operate. We've got a pool of electrons of negative charge that can move to the left, but it's acting as a blocker for stuff moving to the right. So that's what's going on there with diodes. Now, LEDs, light emitting diodes, is this sort of setup, but you're constructing the diode so when these electrons start filling in the holes, as in we've got movement into valence band holes, that combination, that movement to a more stable state, as in a decrease, we're going to a more bound state. So think of what's happening with our energy. If we're going to a more bound state, we need an energy release. So light emitting diodes are just set up so that energy release from an electron and a hole combining is a photon which is coming out as light. So it just follows on naturally from the operation of a diode. Right, the last one I'm going to talk about, because I mean you could go on all day in electronics about the role of semiconductors, but transistors. One of the most revolutionary pieces of engineering in the history of science. I mean, pretty much all of the electronic world that we live in is built around transistors. Now, they're not easy to understand, but let's try and build some kind of basic picture here. Now, there's a number of things that transistors can do, but two of the main ones is they can act as amplifiers, as in we can take a small current in one place and use that to initiate a large current somewhere else, and they can act as switches. And switches are great because well, that means we can operate in binary. We got on and off, we got 1 and 0, and this is the foundation of computation, calculations, and everything else. So this is why transistors are so important, because of these two effects. Now, let's see if we can get a handle on the basics of operation anyway, even though this won't be that easy. Now, so in diodes, we've already encountered this PN junction. And in transistors, we're adding in another junction. So we might have an NPN, or we might have a PNP junction. So let's look at an NPN junction. So you'd have your N, then you'll have P, then you'll have N again. So we're going to have two depletion zones here. We're going to have one there, we're going to have one there. And then we get three connectors going into this transistor. We've got the collector at one end, we've got the emitter at the other end, and then in the middle, we've got the base, which might then be connected off to, some other wire or something like that. And this is why, when you open up like an old TV or some other electronic device which has got larger components, the transistors, these are the things that you see with the three prongs on them for collector, emitter, and base. Now, they can be really, really small. I mean, there's billions of these things on a computer chip. It's mind-boggling how they can end up making transistors that are something like 50 atoms across or something. It's just nuts, but they come in a range of sizes, and you can see these connections. As I say, if you start doing electronics at home, then the transistors will be big enough that you've just got 3 wires going into this semiconductor junction. So what is actually going on with all these bits then? Like I say, we've got these depletion zones at the boundaries, and as we saw with the diodes, these act as sort of insulating buffers when there's nothing else going on. So they're blocking current when things are just sitting around. But now we've got these different potential differences here. Okay, we've got a potential difference between collector and emitter, but we've also got a potential difference between collector and base, and then between base and emitter. So a way we can overcome this double depletion zone that we've got here is if we get a particular voltage here at the base, which we can achieve by passing this, a small current along this connection at the bottom here. We can have a small current at the base with a particular potential that then means we're more or less given enough push, a bit like we did with the diodes, that we can then open up the path from collector to emitter. And that means we can have a small current down here, a little I going through the base that the base is connected to, which can open up the floodgates for a larger current going from collector to emitter. So this is how it's acting as an amplifier. Depending on what's going on at the base, we can potentially open up a larger current. That's also really, if you think about it, a switch. This is all going on with DC here, with what we're using in electronics. And we can have, well, is the current flowing? Is the current not flowing? We've got an on and off. We've got a 0 and a 1. We've got our binary going on there. So that's a real broad brush picture of how this double junction, this NPN or even a PNP, can act as both a current amplifier and a switch. And these three connectors are what you see on circuit diagrams, where you get things that look like this. This would be your symbol for your transistor. This would be an NPN one. This is the base that we've got here. Then we've got collector and emitter going on here. The direction of the arrow is telling us about the flow from collector to emitter, and it depends upon which type of transistor we've got. So if you've got the arrow pointing that way, it's NPN. If it was pointing the other way, if it was going that way, then we'd have a PNP junction there. So yeah, they're the symbols that you see on the more complicated circuit diagrams that we won't really be looking at, where you've got transistors involved. As I say, they're pretty complicated. I mean, I don't know enough confidently about electronics. I'm not an electronical engineer to get into analysing circuit diagrams with transistors in, so I'm not going to go any further than that. If you want to know more about transistors and how they're put into circuits, then search someone else out on that front. But this is just giving a high level overview of transistors, as I've done with a high level overview of semiconductors in general, because this is practically non-existent in pre-university physics. They're dropped in as being these things that exist along with these amazing components that they're essential for, such as diodes, but they don't tell you anything about them at all, in my experience. So hopefully this is at least giving you something to build on. If you then go off to university or and do some electrical engineering or something like that, then obviously you'll study these in much more detail. But hopefully this is giving you a flavour of what's going on and why semiconductors are so important.